Hello, my name is Jacob Eisenhart, and I'm the team lead for the high accuracy, ultra low cost sensor array team. Other members on our team are Alex Ferlin and Michael Moldovan, who are working on programming, Michael Kishler, who's working on testing, and also Tony LaRosa, who is working on our hardware design. Our team is located in Nantes, France, which is southwest of Paris along the coast of France, and we partner with a Grande École or graduate school called ONIRIS. We work with Dr. Ave in their food science department to build a data acquisition unit for testing tunnel ovens and also for food production. So our project consists of two parts, a sensor array and a thermal barrier. Our sensor array is used to take the temperature of the oven every second so it can be used to calibrate the oven, and our thermal barrier is used to house the sensor array so that it can be protected from up to 250 degrees Celsius of the oven. For our project, we have a thermal barrier that consists of a wood box covered in aluminum tape and then also has a layer of insulation on the inside and on the top cover here. The goal of our project is to keep the internal temperature of this thermal barrier below 50 degrees Celsius to properly protect our data acquisition unit. For our sensor array, our thermocouple takes in a voltage reading that is amplified by our digital amplifiers and then taken into our Arduino, which is then stored into our Arduino's internal memory. One of our design specs is to have our battery life of at least 30 minutes using a 9-volt battery connected to the Arduino.
Hello, I'm Tony LaRosa, hardware specialist for the team. You just heard from Jake, who gave you a good overview of both parts of our project. I want to go into more design specifications with you. First, some design goals. We wanted to start off with a 30-minute minimum of our Arduino, which means battery life, and its survivability must be 30 minutes to go through the tunnel oven. Secondly, the Arduino must be able to measure off 2 thermocouples and be able to collect data and store that data to an SD card. And then also, some design specifications and goals for our box is that to be able to withstand heat of 250 degrees Celsius on the outside while keeping a cool 50 degree maximum on the inside. This will also have to come at the cost of only allowing 8 centimeters of height, which would be tricky to do, and we're hopefully going to overcome this challenge and make this an achievement. Some assumptions that have come with these design goals is that assuming that the data can be written to an SD card that we're taking, and it does not fill up the SD card or get corrupted in any way. This has been done in the past and is being done currently. It's just a challenge and an assumption that we made in the beginning. The second assumption is assuming that our readings are coming out to be calibrated, our temperature readings are coming out to be calibrated to 1 degree centigrade. So pretty accurate readings for our K-type thermocouples. Third, and assuming that the Arduino will run for 30 minutes on that battery life. One of our design goals is an assumption that it will run, something we have to do more testing on. Lastly, and assuming the collected data can actually be used, and that is not coming out askewed or corrupted, or that this data is actually useful for the customer. Some risks that are involved with our project are that the Arduino might fail or melt, and so that we create a faulty product. And then are not properly cooked bread, since this is going in to calibrate tunnel ovens. So an external risk is that we create this device which does not calibrate correctly, which is reading correctly, spitting out data correctly, but in the end, something has failed, and we have our customer calibrate their ovens wrong, and they're creating uncooked bread or overcooked bread, so which costs them money. And then spinning off that, just collecting wrong data, and so we're spitting out wrong data. So that is a huge risk that we're making efforts to avoid and to calibrate our prototypes so that these risks can be mitigated. So we have done a lot of testing to be able to get to the design and prototyping point that we have been. I'm just going to run through a few of those tests with you now. The first test is a hot water, cold water test. And this is to calibrate our thermocouples on our prototype for see if there's any issues with the thermocouple amplifiers, the relay boards, and if we can find a temperature drift that we can calculate, hopefully a linear one. So what that was taking cold water and our Vernier Lab Pro and our prototype thermocouples and putting them in here together to make sure they're reading a very similar temperature. And if they're not, what are we doing wrong? Then we have to figure out problems, if there is a problem, with our prototype and troubleshoot it. Next, we go to hot water. Boiling water test. Do the exact same, see what our measurements are. See if there's a temperature drift. See if we can calibrate it that way. So that was the first test. Was for our thermocouples to make sure they were reading correctly. Our second test was using a phase change material in this box, an ice pack. So we put an ice pack and this thermocouple here in this box, and then we put it in our test oven, which our test oven can go all the way up to 250 degrees C, which is the exact temperature that we need to test for. So what we did is we put it in here. First test was without any phase change material, and let it sit and just read the temperatures so we had a baseline to go off of. And so that we can say that this is our baseline design since it's the best design from prior years, and say how can we make that better. Secondly, we put in the phase change material. After we put it in, put it back in the oven, and we run the same test to see how long before the internal temperature reaches 50 degrees C, which is our max point, and then with the outside being 250 degrees C. So, a third test that we ran is the low-cost barrier, like internal temperature calibration. So we want to calibrate the thermocouple relay boards or amplifiers because they have an internal temperature sensor. And so to calibrate those with this larger prototype LCB, low-cost barrier, and to make sure that those on the temperature sensors on the board are reading correctly to what the thermocouples are reading in and to what the Vernier Lab Pro is reading in. So we want to compare all three of those values for the internal temperature and to see if there's any variation. We still have a lot of work to be done and a lot of tests to be ran on our prototypes and more fabrication to be done to meet all of our design goals. So going forward, we're hoping to complete more prototypes in the coming weeks before we leave France from our study abroad. Work with ONIRIS on testing and calibrating our LCA and LCB to make sure that those are up to their standards and their design specifications. And then using a removable storage device. So this would be a lot easier and simpler than having to plug back in the Arduino, but is also another component that works against us in the size. So that is something we're hoping to overcome and to maybe find better solutions for. And then designing our systems to be a little more user-friendly. And then in the end, it's something that customers and consumers are going to want to use and will find it easy to use. And with that, creating multiple designs and final designs for different price ranges and for different temperature accuracy levels. So you can buy very, very low cost, but you're going to get 1 degree centigrade. Or you can buy our high-end model and get a further accuracy to an estimated number of 0.5 degrees centigrade. Thank you for this presentation.